Okay, good afternoon to all. So, this is our 13th lecture of the course Fluid Mechanics, and in the previous lecture we have started our discussion on the concept of buoyancy, where we have studied about the stability of completely submerged and floating objects. Okay, and one conceptual idea we have got that if we are having the floating objects, then metacenter must lie above the center of gravity in order to have the stable situation. Okay. Now, how to calculate the metacentric height? So, if you recall from the previous discussion, I told that mg. So, distance between metacenter and center of gravity, mg is nothing but called as the metacentric height. Okay. And if metacentric height is positive, then we will be having situation of stability. If it is negative, then it will be unstable situation. So it means that for a stable situation of a floating object, metacenter should lie above the center of gravity. Okay. So now we will try to see the mathematical formulation, like how we can calculate the metacentric height. So typically what we can do, we can consider one water line. So water line, basically the free surface of water which interacts with the body, that is something which is called as a water line. Okay. So typically this type of analysis, whatever I am trying to show you over here, this is typically used by naval architects in actually basically because ship etc. whenever they are designing, then they try to keep the design of cross section in such a way so that this type of situation of stability is actually satisfied. Okay. So what we have done first, I have considered that, say this is the cross section of a naval architect, this is some ship, and in this cross section, if I initially consider that it is in its normal position. So corresponding to the normal position, I am saying that A and B as well as C and D both are actually coinciding. So if I take the reference from these 2 points, then I can say A and C are coinciding and B and D are coinciding. Okay. Now, if I have given certain deflection to this, so say I have rotated it through certain angle theta. So once I rotated it through certain angle theta, then my water line is remaining horizontal only, which I have depicted with letters A and B. But if I see the axes which are actually fixed on the cross section of the shape, okay, so these axes are also actually tilting with the cross section of the shape. Okay, so if I fix the axis, then my new axis have become C and D, which is nothing but showing the x direction, and perpendicular to this I have nothing but the y direction. Okay, let's consider that in the original situation this was my center of gravity and this was my center of buoyancy B. In the new situation this is G and this is B dash. So now if you see, earlier this was the amount of volume submerged in the water was symmetric. So as this was symmetric, that's why my center of buoyancy was also lying on the line of symmetry. Now if you see, when we have tilted this, more volume is submerged from the rightward side. So as it is submerged from the rightward side, so my center of buoyancy has also shifted towards right. Okay, so distance from B to B dash I am calling it as x bar. Is this point clear? Okay. Now what we have to do is we have to determine that how to calculate this distance MB, because MB is something which is or in other words I can also calculate MG. So my interest is in calculating either MB or either MG, any of the quantities. Okay. So to calculate this, I will try to utilize over here the concept of moment of area. Okay, so moment of area concept we will be utilizing, or in other words I can call it as moment of inertia also. Okay, so what I will do, let's consider that x bar is my coordinate of the new center of buoyancy. Okay, so what I can do, I can write that x bar times submerged volume. Now I will be writing the submerged volume. So can you tell me which part of the volume is now submerged in this tilted situation? So if you can see A, O, B, D, E, this portion now represents nothing but the submerged volume of this particular object. Okay, so now I have written over here that x bar is my center of buoyancy, and now I am writing total submerged volume of this, which is nothing but equal to A, O, B, D and E. So this is the situation. Is this point clear? Now this must be equal to integral of x into elemental volumes. Okay, so if you see, I want to take here help of symmetry in order to simplify my situation. Okay, so if you see earlier how much portion was submerged, so this hatched portion over here, this was the submerged volume. Okay, so if I consider in new situation also the same amount of submerged volume, then I can consider this entire hatched volume. So that will be nothing but x times dv, where dv is my volume integral, but this volume integral I am considering for this hatched portion. So hatched portion in the new figure is actually from C, D, C, O, D, E, A and again C. Is this point clear? So integral I have to now consider for the point E, O, D, E and A. Is this point clear? So this much volume I have now taken. When I have taken this much volume from this point to this point, now you can see this portion OBD. OBD volume is also submerged. Okay, so now I have to do integral OBD x into dV. And because earlier I have taken this total volume, so this portion COA, this is nothing but extra volume which is included in this particular first term. Okay, so as this extra volume is included, I have to subtract it over here. So minus x times dV over COA. Is this point clear? So now what I am saying is actually my submerged volume times center of buoyancy is nothing but x times elemental volume, and these elemental volumes integration I have chosen in such a way so that it is becoming my equal to the net submerged volume. Okay, so movement of the submerged volume I am considering for elemental basis, and that I am equating equal to the center of buoyancy times my submerged volume. Is this point clear? So this is nothing but the approach for estimation of the center of buoyancy when we are having the asymmetric situation. In this body now situation is asymmetric, because in this previous portion it is completely symmetric situation. I can easily determine my center of buoyancy, but when I have tilted it, then the portion of submerged volume is not purely symmetric. Okay, so that is why we have to utilize this type of approach for determining the coordinate of the center of buoyancy. Is this point clear? Now I have considered it, say it is at okay, so now what I can do, I can write that x bar times of submerged volume is equal to, can you tell me what will be x dV EO dEA? So I am considering about line of symmetry movement of the volume. Okay, x times volume, so it is nothing but movement of the volume. I am considering about line of symmetry. So if I see about this line of symmetry, all the volumes are equally distributed in upward side as well as in the downward side. So here movement of volume from both the sides will be cancelling actually each other, and ultimately I am getting this first integral to be 0. Is this one clear? Because about this line of symmetry, my volume is equally distributed in upward side as well as the downward side. So that is why I will be having this first integral equal to 0. Now I have to consider plus x times integral of OBD. So let's consider that I have some element over here, and the area of this element is nothing but dA. Okay, dA is this area of the element, and this element I have taken at a distance x from this point and say the thickness of the element is dx. Okay, so if you see, this point is nothing but EODEA. So E, this is E basically, sorry, not E, yeah, this must be C. I have written it wrongly. CODEA. So this point is C. So this is my line of symmetry about which I am taking this moment, because my x distance is being measured from this line. Okay. So if you see, for this entire control volume, above this line of symmetry and below this line of symmetry, both sides we have the same amount of volume. Okay. So any elemental integral times distance will be cancelling out from both the sides, because in this side x will be positive, in this side x will be negative. Okay, so that way the movements will be cancelling. Okay, so this is for the first integral part. Yes, yes, please. Yeah, so OBD I have included in the second term. Right now I am talking about only the first term, which encounters CODEA. Let me again highlight this with the other color. I am talking about right now in the first term about this volume.
So the volume on the left side is less than the
Volume of the left side is
less than the volume of the right side.
no. Right now I am not considering how much it is submerged. Okay. For submergence only, for determining the submerged volume only, I have included the second and third term.
So the volume which would be adding the moment about this line of x would be the means we need to consider the amount of water so that it would
Yes, we need to consider the submerged volume. But if you see how I have calculated the submerged volume, in first term I have included this entire enclosed volume. Then you see the second term. In second term I have added this wedge portion. Then you see the third term. In the third term I have subtracted this portion. So then it has become now our actual submerged volume. Okay. So right now when I am talking about 0, I am only referring to the first term, which is representing the symmetric distribution. Understood or not? For our simplicity of calculations, we cannot directly calculate this entire movement of the submerged. So what we are taking the help of symmetry. So first we are considering what was in the original situation plus what addition has come minus what portion we need to remove that has now come out of the water line. Understood now? So that is the reason for the first term, because we are only talking about the symmetric situation. So that's why this is becoming 0. For the second term, I am telling that let me consider that at a distance of x, I have nothing but one small element of elemental area dA and thickness dx. And let me consider that the width of this element normal to the board is L. L is what? Width, which is normal to the board. So if L is width, can you tell me how much will be dV of this elemental volume? How much will be dV? dA times L. Understood? So L times of D. Is this one clear? Minus integral of, whenever you will be moving to this side, now you have to consider element over here. And because this body is, if theta is angle this side, here also angle is theta only. So I can simply write in a similar fashion L into D. Is this point clear? But whenever I am writing this L into dA with this x, now I have to put, okay, that I will explain you later. So this is my point now, COA. Up to this point, is it clear? or anyone is having any confusion? Please tell me, this is very important step. Okay, so now we will be having x bar into submerged volume is nothing but equal to integral OBD x times L. Now dA, what I can do, this is my area dA. Okay, so how it is distributed, you can see this is water line. Okay, and this is my wedge section, and this is area which I have considered. So this is dA area. Okay, and this angle is theta. It is at a distance of x. If this distance is x, can you tell me how much will be this dimension from here to here? It will be x tan theta. Okay, x tan theta will be this dimension, and dx is the thickness of the element. So dA I can write x tan theta into dx. Is this one clear? Minus integral over COA XL into, now in the opposite direction I have to go. Okay, so in the opposite direction my this vertical distance will be becoming minus x tan theta. Understood? Because in opposite direction this is my x axis, I am going below the x axis, so it will be minus x tan theta times dx. Is it clear? Now if you see from here, I am getting that x bar into submerged volume is equal to integral x square. Okay, tan theta let me take common from both. So tan theta is common from both. Okay, so it is nothing but x square times L dx plus x square times L dx. Is this one clear? Now can you tell me what is L dx? Dx is the thickness and L is width. Yes, so L ds I can say the area which is parallel to the water line. Okay, so I will be calling area planar area which is parallel to axis or parallel to x axis. Okay, so I can call that x bar into submerged volume is nothing but equal to tan theta times x square of dA water line. Okay, so now what has it become? Area in a plane multiplied with square of distance. Second, moment of area, or I can say it as moment of inertia, area moment of inertia. Is this one clear? Because it is half is for this portion, this integral, half is for this integral. So ultimately for total water line area, this area, in original situation this area, this is the water line area. Okay, when situation was normal, this is the water line area. So in normal situation, whatever my water line area is there, its second moment about origin, because this is O point, this is O point over here. Okay, so about point O. So from here I can say that x bar into V submergence is nothing but tan theta into I naught. Point is clear? Here it is very, very important to know what is I naught. I naught is nothing but area moment of waterline area moment of inertia about tilted axis. If you are considering the tilted geometry, then tilted axis, for normal situation, this axis. Okay. Okay, up to this point, is it clear? So from here I can clearly say that my x bar divided by tan theta is nothing but equal to I naught divided by submerged volume. What is clear? Now you relate it to point MB. So this distance from here to here is my MB. Okay, and this distance is x bar, which is perpendicular distance to this, and this angle is theta. So this is perpendicular, this is base. In terms of tan theta, what will it will be? From this geometry, x bar by MB equal to tan theta. So from here, m into v, let me write it in vector only, distance from m to v. So mv vector has become, so I will be putting bar over this in order to represent the vector sign. It has become x over x bar over tan theta. So from here I can say that my distance between center of buoyancy, original center of buoyancy, when situation is symmetric, okay, that distance is nothing but equal to I naught by V submerged. Is this point clear? Now, interesting point is, somewhere on this line only my center of gravity will be lying. Okay, so MB I can write as mg plus gb, which is equal to mg plus gb distance. Okay, so from here my mg, which is called as metacentric height, that is nothing but equal to I naught by volume submerged minus gb. Okay, now depending upon the relative magnitude of gb and I naught by v submerged, mg can be positive, it can be negative. So if mg is positive, then we have stable situation. Okay, now for a situation where my gb is negative, if gb is negative, then negative negative will become positive and mg will be always positive. What is clear? mg will be always positive. If mg is becoming always positive, for that situation, then I will be finding that this is nothing but if gb is negative, this is always a stable situation. Okay, so when you tilt your ship, then what happens? Determining its different parameters, for example, new center of buoyancy, all these things becomes very complicated. So that is the reason, through this derivation, with reference to the symmetric situation of the ship only, we can predict all the parameters. Okay, what is MB over here? If you see, B is not the new metacentric height. B is the previous center of buoyancy. Okay, so B is the previous center of buoyancy when situation was symmetric. Is this point clear? So it means by just knowing the previous center of buoyancy by just knowing the symmetric situation waterline movement of area, fine, and this distance between center of gravity and original center of buoyancy, I can determine the value of energy. Is this point clear? So for this, I need not to first locate the center of buoyancy for new situation and then go back and substitute it. Okay. Is this point clear? So that is the benefit of doing this mathematical manipulation, because the final formulation which we have got, that is nothing but which can be obtained from the stable symmetric situation. Okay. Is this point clear? All are clear with this idea? Okay, let's move then to next topic. So now we will talk about, say I have a body, fluid body, which is subjected to acceleration. Okay, so say I have a tank, and this tank was originally filled with water having some height h naught. This was the original height h naught. Okay, and now I have given some a amount of acceleration to this. Okay, and these are, say, this is the origin, this is x direction, this is z direction, and of course we have the presence of gravitational field over here. Okay, now whenever I will be giving acceleration, of course depending upon the magnitude of the acceleration, I will be finding that this free surface will be disturbed. Okay, so if you have a water bottle, if you carry it in your hand and then move with some constant acceleration, you will be finding that free surface will take some angular position, at some other angle it will be actually, okay, balancing each other. So let me consider that, say it has acquired a new position, something like this, which is at an angle theta. Okay, so we have to determine that depending upon the magnitude of the acceleration, how much will be value of theta, whether we will be having a straight free surface or whether we will be having any curved thing. Okay, so that's something which we can determine now. Okay, so typically if you see, I have x direction and z direction, and there will be one direction normal to the board, which is y direction. So I am considering that I don't have any sort of motion in the y direction. Okay, so y direction is there is no acceleration in the y direction. So acceleration is only in, because of this a vector, I will be having some component in x direction, some component in z direction. So only these are the components of acceleration. Okay. So now, if I consider this situation, can you tell me what will be the forces now which will be acting on this body? First, you tell me, will this be a situation of fluid statics, or do we have some sort of transient dynamic thing also? Initially, whenever I am having the free surface, it is in horizontal situation. Then I started moving it with some acceleration, constant acceleration a. But it will not automatically come to constant acceleration. Before coming to constant acceleration, it will be having some transient phase also. Okay. So what we are considering, we are eliminating that transient phase out of our analysis, and we are now only talking about the second situation once it has achieved the constant acceleration. Is this one clear? Okay. So once it has entered to the new constant acceleration position, then there will be change in free surface, orientation of the free surface, but once again, whatever the new position it will be taking, it will remain fixed to it. Okay. So once again, a new static equilibrium condition is actually established. Okay. So if you recall, when we started the fluid statics, I have given you different forces. One is the, if I write on per unit volume basis, pressure force plus viscous force plus body force, that is equal to rho into acceleration vector. This is the equation of motion. Is this one clear? This is my equation of motion. Now I have to impose over here the conditions. So what are the conditions? First is, if after reaching acceleration A also it is static, then viscous force will be 0. Okay. So now, but it is having some acceleration A over here. So I have to consider pressure force and body force. Okay. So now let me write this equation in individual directions. So if I write in x direction, then minus del P by del x is my pressure force per unit volume. Okay. What is body force? Rho gx, that must be equal to rho into acceleration in x direction. Okay. So gx is 0, there is no gravity acting in x direction. So I will be getting from here that in x direction minus del P by del x or plus del P by del x equal to minus rho ax. What is clear? Then if I talk about the y direction, then del P by del y will be equal to 0, because in y direction there is no acceleration, there is no gravity. Okay. So del P by del y will directly be 0. Then if I talk about the z direction, then minus del P by del z plus rho gz. Now in z direction I have gravitational field. Okay. That is equal to rho into az. So from here I will be simply getting that. Okay. Now what is gz? Gz is minus g. It is acting in downward z direction, so that's why it is minus g. Okay. Minus g equal to rho a z. Now from here I will be getting del P by del z equal to minus of rho times az plus g. Is this one clear? Anyone is having any doubt? Okay. So now if I talk about the situation of no acceleration, then ax equal to azb will be 0, and along with this if I also introduce a situation that I have microgravity, there is no gravitational field present, then g will be also 0. So for this first situation, if all these things are existing, my gradient of pressure means pressure, gradient of pressure, del P by del x, del P by del y, everything, del P by del z will be equal to 0. And for such a fluid element, at each and every point pressure will be same. Is this point clear? Okay. However, if for this situation you measure the pressure, you are having a liquid element which is satisfying all these situations. For that, if you measure the pressure, still there will be slightly higher pressure than the atmospheric pressure. Why? Because of the surface tension. So surface tension is holding that liquid element. So because of that, inside pressure will be slightly higher than the outside pressure. But with changes in x, y and z direction, there will not be any change in pressure. So the meaning is, if I have a spherical liquid drop, for this spherical liquid drop, even if I put a pressure sensor here, 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 anywhere if I put a pressure sensor, everywhere I will be having the same value of pressure. Okay, like this. So this is this situation. Second situation, I can consider that I have freely falling body. What will be the situation in freely falling body? Freely falling liquid volume. So for a freely falling liquid volume, there will not be any acceleration in x direction. Acceleration in z direction will be how much? minus G. Now if you go back to the equations, del P by del X will become 0. Second situation, del P by del Z. This is G, gravitational field, and this G is acceleration of the body. So acceleration of the freely falling body is minus G. So del P by del Z is also 0. What is the meaning of this? There is once again no pressure gradient in a freely falling body. So if you have a drop, okay, and if you consider that drop you have started from this point with no initial velocity and allowed it to fall freely, considering that the air drag is negligible, what will be the pressure across the different surfaces of the drop? Same. Only it will be slightly higher than the surrounding pressure. That is because of surface pressure. Okay. So that is the reason why in case of a freely falling object we experience actually weightlessness. Okay. If you consider you are inside a lift, 100-story lift, and if rope is broken, what will be happening? Lift will be falling with acceleration equal to minus G, and you are standing inside that, you will not experience any weight. Whenever lift goes down, our lifts are not having that much high acceleration, but if you see, whenever lift goes down, then slightly we feel decrease in our weight. Whenever it rises upward, then we are having increase in the weight. That is what we experience. Okay. Okay. Now it is important to know that we are mainly interested in if we are having acceleration A, then what will happen to free surface. Okay. So we have got two quantities. One is, so if I don't consider the special cases and if I go back to my original situation, if I go back to this original situation, then I have now del P by del X equal to minus rho AX and del P by del Z equal to how much? Please tell me. Minus rho AZ plus G. Okay. So if I have to write down the total pressure dP, now pressure has become function of x comma z because y derivative is equal to 0. Okay. So if I have to write down total pressure, that will be equal to which will be becoming minus rho AX minus of into dx minus of rho times Az plus G into dj. Point is clear? So from here I can simply write that, okay, it is fine. So this is my equation of pressure. Anyone is having any doubt with this equation? All are fine? Okay, now what will be happening? This was my original free surface. Now free surface has tilted. Okay. What do we mean by free surface? Free surface is nothing but a liquid surface of constant pressure. Corresponding to this only we are having isobar. Okay. So I can say that when my pressure will be, free surface will be tilting like this, any point I consider on this free surface, everywhere I will be having nothing but outside pressure P0. Whether I talk about this point, whether I talk about this point, whether I talk about this point. So along the free surface, I will be having the existence of isobar. So for a free surface, dP will be equal to 0. This is for free surface. Is this point clear? For yes, at free surface it will be experiencing because it is tilted like this. Okay, so I understood your doubt is that one end should have high pressure. let me tell you. Free surface is now like this. Okay. So if you measure pressure at this point, then what will be pressure? This is P naught, say this height is H1. What will be pressure here? P naught plus rho G H1. If you calculate pressure at this point, what will be pressure? P naught. At this point, P naught plus, what is above this? Air. Vertically above this is air, which is of negligible density. So rho gh can be neglected. So ultimately the pressure acting at this point is, so everywhere over the free surface pressure is P naught. Sorry, tell me. Okay, point is clear. So everywhere pressure at the free surface is P naught, because above the free surface at every point we have air, for which rho gh is negligible. Okay, so for free surface dP is 0. So if dP is 0, then for free surface I can say that rho ax into dx equal to minus of rho az plus g into dz, and from here rho will be cancelling out. I can say that dz by dx for free surface is nothing but equal to minus of ax by az plus g. Okay, now if I say that my surface is having what? If I say that my surface is having constant acceleration, so it means that ax and az are constant, g is also constant. So this dz by dz is nothing, dz by dx is nothing but a constant, and this will be equal to, what is dz by dx? Slope. Okay, tangent to a point on any curve. So tangent to a point on any curve is equal to slope. So this must be equal to tan theta. So have you understood how to calculate the, so this theta we have got as dz by dx for the free surface. Okay. So once I know the acceleration values, I can substitute over here the acceleration values and I can simply calculate the angle at which my free surface is. Point is clear? Now next is, if you have to calculate pressure at different portions within the fluid for accelerated object. So how you can calculate? This is dP. Okay. So if you consider that you will be integrating dP from P naught to P, that will be equal to minus rho ax, its integral over x from, say, origin of x is 0 to any other value x. So what I am considering that in this situation, if this is my origin, let's consider this is at this point x and z will be 0, 0, corresponding to this, say my pressure is P naught. So with reference to this pressure at any point I can find if I know the value of x and z. So how I can calculate this integral from 0 to x and then minus, is it plus or minus? Minus. Integral 0 to z rho times az plus g into dz. So this will be P minus P naught equal to minus rho ax is constant into x minus of rho az plus g is constant into z. So by just knowing the x and z, the location of any fluid element, okay, at any point within the fluid with reference to the origin, by considering P naught pressure at the origin, you can determine the value of pressure. Is this one clear? Anyone is having any doubt with this? Now one interesting point I want to show you over here. If you see the gradient of P vector for this situation, so gradient of P vector will be nothing but del P by del X plus del Y plus del P by del Z, K cap, J cap and I cap. So what is del P by del X? minus rho ax, okay, del p by del y is 0, then what is del p by del z? Minus rho az plus g into k cap. Okay, so ultimately if you see, let me draw with vector addition. This is your acceleration vector a, okay, and this is your gravity vector. Let me draw it over here. This is your gravity vector g over here, okay. So if you calculate vector g minus a, then how it is oriented? This is vector g minus a. Is this one clear? This is vector g minus a. Now you can see that in whatever direction we will be having g vector minus a vector, that is nothing but the direction of the gradient of the pressure. Okay, so if gradient of pressure is oriented in this direction, then our constant pressure surface should be normal to that direction. We have discussed earlier also. Okay, so that is the reason that my free surface is oriented like this, because this is nothing but the direction of g vector minus a vector, which I can say the direction of the gradient vector, gradient of pressure. Okay, so in whatever direction gradient of pressure is oriented, our free surface will be normal to that. Means the surface of constant pressure value will be normal. Okay. So now we will talk about next example, which is if my fluid body or liquid body is subjected to rotation. Okay, so situation is, say I have one object, I have one container, and in this container I have some liquid which is resting at height h0. Okay, now I have started rotating this container with some angular velocity omega. Okay, so if I rotate this container with angular velocity omega, once again the same thing will happen. First I will be having motion, relative motion between the fluid layers, and after that all fluid layers will become static and it will move like a rigid body. Have you seen a water container, rotating water container? What happens to the free surface? It becomes some curved, something like this. Okay, so if I draw the free surface over here, it must look something like this. Is this one clear? This is the free surface. So let me consider that this coordinate is r, this coordinate is z. Okay, and after we have given it constant angular velocity, so whatever the lowest critical height at the center point it is having, that is hc. And let's consider at any arbitrary point the height of this one with reference to origin is actually z. Fine. Now this type of situation, what we have to do, we have to determine the equation of this free surface. Okay, and to understand this situation we can go into the cylindrical coordinate system. So r and z I have taken, I will be having another direction as theta direction. Okay, so theta will be nothing but I will be rotating this cross section 360 degrees. Okay, so if I take that azimuthal direction for the motion of a fluid element in the form of a rigid body, what I will be having? I will be having any variation in the z direction? Sorry, in theta direction? No. So I can clearly say from here that del P by del theta equal to 0. Okay. Now in terms of r direction, yeah, so what I am trying to, okay, let me explain one by one. So I have to analyze this situation in nothing but cylindrical coordinate system. Okay, so in cylindrical coordinate system, if you see, this is a two-dimensional view of the surface, but in reality it will be forming a three-dimensional surface. Okay, and if you take two-dimensional plane at any angle, everywhere you will be finding the same profile for a symmetric situation. So that is what I am saying, that everywhere my profile of the free surface or profile of the properties will be same. So there will not be any change in properties if I keep on rotating the plane at any angle. So that is the reason I am writing del P by del theta equal to 0. So angular variation is 0. It means no angular variation. Is this point clear? Now, what I have to do next? Del P by del R. Can you tell me? Will be having any del P by del R? So minus del P by del R is the force because of the pressure. This must be equal to, now body force in R direction, there will not be any body force. Okay, because gravity is acting in Z direction. This must be equal to acceleration. So whenever you are having a circulating object, then we are having nothing but the centripetal acceleration. Okay, if you are having a something tied to a thread and if you keep on rotating it, it experiences nothing but a centripetal acceleration. So what is the magnitude of centripetal acceleration? Mr omega square for a rigid body. So on per unit volume basis it will be rho r omega square. And this centripetal acceleration will be acting in inward direction. So that's why it is coming. So r is positive in outward direction from the origin. So it is coming in inward. So it will be having negative sign. Minus rho r omega square. Fine. Then let's talk about the z direction. So minus del P by del z will be how much? Minus del P by del z will be minus del P by del z plus rho g will be equal to rho times a, any acceleration in z direction. Okay. So from here I will be finding that acceleration in z direction in this situation is not there. So az is 0. So from here I am getting del P by del z equal to rho g. And here also negative negative will cancel, del P by del r equal to rho r omega. Is this one clear? Now if I have to find out the total pressure, pressure is function of only r and z. So dP will be del P by del r into dr plus del P by del z into dz, which is equal to rho r omega square into dr plus rho g into dz. Once again, for this entire free surface, what we will be having? For the free surface, we will be having zero pressure, same pressure everywhere. Okay. So dP will be 0 for free surface. So now what I can write? Rho r omega square dr equal to minus rho g dz. From here dz will become minus r omega square by g dr. Okay. Now let's integrate. If I integrate dz, then what I will be getting? Dz I will be integrating from z0 to z. Okay. Because I am integrating over this surface. So let's consider at this point my coordinate is z0 and at any arbitrary point it is z. Okay, so z naught to z I will be doing integration, and for r it will be from 0 to r, limit of integration. Or let's not do that, we can do it in terms of determining the constant, that also we can do. Okay, so if I do integration of this, then I will be getting integration of dz is z equal to, what I will be getting over here, tell me. Minus r square omega square by plus constant of integration. Okay, now I can say that when my r is 0, this is the point for free surface at which r is 0. What is z? Z equal to hc. Okay, so when r is equal to 0, then z is equal to hc. So from here, what I will be getting? C1 equal to hc. So from here I will be getting that z is nothing but equal to hc minus r square omega square by 2g. Fine. So can you tell me what is the shape, what is this equation? This is equation of parabola in 2D. In 3D it will be becoming a paraboloid. Okay, so it means that if you take the projection of this free surface for a container which is subjected to rotation, you will be finding this is nothing but forming a parabola as the free surface, and in 3-dimensional case it will be a parabola. Okay, now interesting point is this hc is something which is actually depending upon this value. Okay, we have to independently define the parameter hc. So how we can determine independently parameter hc? If I do the volume conservation. Okay, so if I say that whatever was the volume below this height h naught, so below height h naught, if r is capital R is radius of container, then what was the total volume? Pi r square h naught. Now for this curved surface, how I can determine the volume? For curved surface, I can take any element over here, I can determine the volume for that element. So element is at, say, radius r, so circumference of the element will be 2 pi r, dr is thickness of the element, so this is my area, multiplied by z is height of the element, and this integration if I do from 0 to r, then I will be getting nothing but my total volume below this curve. Is this point clear? How to calculate total volume below the curve? 2 pi r into dr is its area and z is its height from the origin. Okay, so substitute the value of z over here. So if you do so, what you will be getting? 2 pi r dr into, in place of z you can write hc minus r square omega square by 2g. Okay, so if you do integration, you will be finding that pi r square h naught equal to, tell me, 2 pi hc capital R square by 2, okay, minus, tell me, pi r power 4 omega square divided by 4g. Fine. So from here h naught will be hc minus pi will cancel, r square omega square by 4g. So hc will be h naught plus Okay, now let's substitute it into Z. So Z will be H naught plus R square omega square by 2G minus, sorry, by 4G minus small r square omega square by 2G. And ultimately I will be getting Z equal to H naught plus R square omega square by, or even omega square by 2G into R square minus R square by 2. Okay, so this is my equation of the free surface. Now how to calculate the pressure? So for calculating pressure at any point, we have to integrate this equation. Okay, so once again I will be considering that, say at origin my pressure is P naught, where R is equal to 0 and Z is equal to 0. Okay, so now if I do integration, then what I will be getting? P minus P naught equal to rho omega square R square by 2. This is with, okay, positive sign, plus into Z. Okay, so this is my pressure at any point with reference to the P naught. Now in this previous equation, if you substitute small r equal to capital R, then you can determine the value of Z at the corner. Similarly, if you substitute over here the value of R and Z at any point, you can calculate the pressure. But one point is very clear, that whatever the point, the way our free surface is varying, pressure is also varying in the similar fashion. Okay, so this rho g z is coming because of the hydrostatic part, plus because of the rotation of the fluid, this component is actually coming, which is varying the pressure in radial direction. Okay, and you can see that in radial direction pressure is varying in which way? Parabolic way. Okay, so the meaning is that if I draw isobars for this situation, then I will be finding that if this is my free surface, then free surface is mimicking some pressure P1. Then if I draw any other line parallel to free surface, that will be mimicking some pressure P2, which is less than or greater than, which is greater than. Then similarly I will be having some other line. So this is how my isobars will be looking. Okay, so from this point, one important observation is, if you are at same elevation, if you don't change the elevation, then rho g z component is not changing. Okay, so if you are at same elevation and if you move towards the outer side, then you are entering towards the higher pressure side. Okay, so this is a situation, generally what we say, that if I am on same elevation, then pressure is not changing. But in this situation, what is happening? With elevation, hydrostatic component is same, but we have some component because of the rotation of the fluid element. So because of this, if I am at the same elevation but I am moving in the same elevation in radial direction, then also my value of pressure is actually changing. Okay, so this is one important observation for this. Okay, so I thought that we will do one numerical problem also. So for the time being, I will just write the problem statement. You can try it by your own. Okay, so problem number 1. Say I have a curved dam surface. So this is nothing but a dam, but this is curved surface, and projection of this curve in horizontal, in this vertical plane is having z naught depth, and in this plane it is having, say, x naught up to this point. So maximum projection in this direction is x naught. Okay. Here I am having some water filled inside this. Here say pressure P naught is equal to 0 atmospheric. Okay. So what you have to do, you have to determine the forces which are acting on the dam, considering that this wall of the dam is having parabolic profile, having equation z by z naught equal to x by x naught whole square. Okay. And what are the forces acting on this? Say any vertical force Fv or Fh, you have to determine, then you have to determine the resultant force Fr and its line of action theta, and at what angle it is or what position it is striking on this wall. That is something which you have to determine. So this is nothing but an solved example problem of your FM White. So what you can do, you can try this problem, and if you are finding any difficulties in solving, then please let me know. Okay. This is solved problem for hydrostatic, the first solved example. Okay, hydrostatic forces on submerged curved surfaces. Please solve this problem, and if you are finding any doubt, then let me know in the next class. Okay.